with a bunch of members from the Candles team, many who are here, and primarily with one of my undergrad or former undergrad students, Zach Reiser, who graduated this fall. A little loud. I'm a little loud. How about that? And divides his time between finishing up this paper with me and touring in a funky jazz band, which is pretty challenging, but he's a good student. So when I think of galaxy evolution, I like to think of the haves and the have-nots. And of this idea, so here we have mass functions from redshift 0 that Eric Bell and I did a long time ago, and if you integrate, you see that the quiescent population has accumulated most of the stellar wealth by the present time, and this has been going on over all of cosmic history, at least since the last 7 to 11 billion years, and I think of it as something I like to call galactic capitalism, or severe galactic capitalism, in which the quiescent galaxies are the population that are growing, even though they're not doing any of the actual work producing stars. And a little more than 10 years ago, Eric and I used the Hubble Space Telescope as part of the GEM survey and showed that this growth was dominated by spheroid-dominated or spheroidal galaxies, early type galaxies, all the same, all synonyms of each other. During the last half of cosmic history, which we could probe from redshift less than 1 to 0 with GEMS and Sloan. Now, this galactic capitalism now has been going on, it seems, from the beginning of cosmic high noon. We think of cosmic high noon. This is a term that either Sandy or Joel coined. Is that true? Pardon?
I thought it was Harry Ferguson.
Oh, Harry. Okay, I should give Harry credit. This is really... Well, it seems like it's not echoing to you all?
No.
Okay, it's to me. So from cosmic high noon, think of this as the time of peak galaxy activity. The growth of the quiescent population has been going through, even extending to before cosmic high noon. And that's coupled with the decline in star production. And to me, I always find these two plots together very fascinating. First of all, you see at the beginning of cosmic high noon, around redshift of 3, the quiescent population only had 2% of its stellar wealth. And it had 4 times less number of stars than the star-forming population. And during cosmic high noon, where we had pretty much a very high constant rate of star formation, the star-forming population, the workers doing all the work, they were gaining in mass, but the quiescent population is still gaining much faster. And then with the decline of star formation over the last half of cosmic history, this flattens out and the quiescent population really takes off. So with candles, we can now really explore the role of spheroidal galaxies, and some of our co-authors already have, during the period of cosmic high noon. I'm going to do it slightly different. I'm going to make use of a very significant team effort to visually classify thousands of galaxies. So we had over 70 postdocs and students and faculty organized over the last 3 or 4 years that classify every single bright galaxy in candles at least 3 times. This is a lot of work. This is all outlined in Jehan Kardotepi's paper 2014. We used the output from all that effort to come up with something you could think of as basically a visual disk to total ratio. And I'm not going to spend a lot of time talking about the classifications. Here, I'm going to use the morphological classifications for the massive 2,800 galaxies in this redshift range from UDS and good south. But there's 2 takeaways about the classifications I want everybody to have. One is that if I look at what we're going to call visually spheroidal galaxies, so these are either bulge-dominated, according to the classifiers, or pure spheroids. These galaxies are structurally, based on Galfit results, distinct from the disky population. They are rounder, they are smaller on average, rounder on average, and they have higher Sirsic indices. The other thing is all the results I'll talk about, the role of spheroidal galaxies in the evolution of massive galaxies during cosmic high noon, it's all robust, whether or not I use visual classifications or an automated selection of early type or spheroidal galaxies, such as a Sirsic cut. Okay, so let's look at these morphological classifications in the stellar mass versus specific star formation plane. So we've broken this into 4 redshift bins of roughly constant co-moving volumes, so we can see the increase in number densities. I have a lot going on here, so give me a second. Splitting, and we actually reversed the specific star formation axis, so star forming's at the bottom, quiescence at the top. We divided the quiescent and star forming population following an idea that Ryan Brennan did in a recent paper in 2015. Basically, we have an evolving quiescent star forming cut, and it's based on a fit to the star forming main sequence, and then it's just 25% of that rate of specific star formation. Another mark here on the dashed red line, just for reference, is another common separator that people have used in the literature, which is 1/3 times the Hubble time at that redshift to show really dead galaxies compared to all quiescent galaxies. And a couple things stand out in this plot to me. First of all, something that Eric Bell pointed out with one of the first Candles papers, when you bin in constant co-moving volume, you could just look at the number of points as you move forward in time, and you can see a clear buildup of the number and density of galaxies. Split into the star-forming main sequence, the buildup of this population, there's more and more as you move forward in time. At every single redshift, they're predominantly disky galaxies, morphologically and structurally, with a smattering of irregular and peculiar objects. I forgot to say that of the massive galaxies that we have classifications for, which is a complete sample over those redshifts 0.6 to 2.5, this redshift range right here, the vast majority of them, the classifiers agreed, were either composed primarily of a disk or spheroidal component, even though they had a choice to do things like peculiar irregular, clumpy, and so forth. And so, at least at the depth of Candles images, it seems like most galaxies have pretty normal light profiles. All right, so the buildup of the star-forming sequence, lots of disks, or disks with small bulges, so disk-dominated galaxies and our visual classification types. And then the little X's that are blue, those are about 10% of all the massive galaxies, which tend to be peculiar irregular. So they're all star-forming. That's not surprising. Structure goes to star formation. And then if you look at the very strong buildup in the quiescent population, that's dominated by spheroid or pure spheroid or spheroid-dominated galaxies. So galaxies where there might be a disk component, but most of the classifiers thought that the bulge was dominating. And so each redshift bin, you're building up very rapidly in number densities. This is seen by other authors, some of Marrow's students. And these are all spheroidal for the most part. Now I want to quantify this dominance of the massive quiescent population evolution being dominated by spheroidal galaxies by looking at number densities as others have. So here we have our 4 bins, and actually took the latest redshift bin and broke it into 2 times because it's actually a pretty wide time step. So we have 5 bins in time, number density. And for now, let's just look at the black dashed line. That's the total quiescent population of massive galaxies. It's building up rapidly, almost a factor of 10 from 11 billion years to 6 billion years. And the solid red line is our visual spheroidal galaxies, which track right along with the massive quiescent galaxies. It makes up the bulk of that growth is by spheroidal galaxies. Now, I will say that there's a little bit of, well, I need to show this right here. The banding here represents different ways of selecting spheroidal galaxies. And so just sticking with the red for a minute, the solid line is the visually spheroidal, and then the band represents either a pure Circe cut or a conservative combination of pure Circe cut and visual classification. And so the one place that the classifications might get a little bit dodgy is at the highest redshift bins. And this is something that Arjen van der Velde pointed out, at redshifts around 2 massive galaxies that are quiescent. A lot of them appear to be disk dominated based on their axis ratios. I also want to say not only that our results of the spheroid dominance, especially at redshifts less than 1.5, contribute to the quiescent growth, is pretty robust or independent to the way that we define spheroidal galaxies. It's also very independent to how we actually select quiescent and star forming. If I move my little split between quiescent and star forming plus or minus 0.3 dex, that gives you the band line right there around the solid red line. And so very independent to that as well. The last thing here is I've showed the number density evolution of quiescent spheroids, and here's the number density evolution of star-forming spheroids in blue in the same bands for the 2 different things, definition and quiescent star-forming selection. And you notice that during cosmic high noon, the star-forming spheroidal population tracks right along with the quiescent spheroid population, and then around redshift 1 suddenly diverges very strongly in number density, becoming less and less important fraction of the total spheroidal population, basically dying off. So I want to spend the entirety of the rest of my talk talking about the evolution of the spheroidal population in a little more detail using a plot that Guillermo Barrow came up with, which I like a lot. We've seen this plot a bunch of times. Here's just the version with the visual classification symbols on it. So again, specific star formation rate here, star forming at the bottom, quiescent at the top. And this is the compactness parameter or mass density within 1.5 powers of the effective radius. So I'm not talking about the inner parsec density, I'm talking about the whole galaxy, because I actually want to see what's going on with some galaxies that puff up at later times. And again, the same 4 constant co-moving volume planes. We have star-forming quiescent, we have compact, and extended split by a value in this parameter that Guillermo used of 10.3. And again, if you just look at the solid circles, which represent the spheroid, or the dark solid gray circles, which represent the spheroid-dominated objects, they populate and move around from redshift to redshift in this parameter space, while the disks all sit right here. And so I'm saying there's a complex evolution of massive spheroidal galaxies, which is in contrast to a pretty boring evolution of extended star-forming galaxies, which is, again, are mostly disky. And you can see they just basically slow down in their star formation rate over time, but otherwise sit in the extended part of the parameter space. What I find interesting, and Guillermo and others have pointed out, is the buildup of compact quiescent galaxies, compact quiescent spheroids. As you move forward in time, they get more and more number density. And then something happens after cosmic high noon around redshift 1. The population seems to slide over here slowly. And this is the observed size growth that many people have pointed out, like Casada and Arjen van der Velde and others. Now, at this conference, we've heard a lot of different ideas about how this is happening, or why this evolution that I'm showing here is happening. And I want to just touch on those for a minute. The first one is, and this one is pretty easy to accept when you look at the pictures, the idea that you take the compact star-forming galaxies and you quench them rapidly and evolve them up to compact quench galaxies. We've seen this idea many times, and so I see compact star-forming galaxies and I see the compact quiescent galaxies building up. So you kill them off, send them up there. That seems to make sense and is not too unusual. The other idea is, how do you make the compact star-forming galaxies? Basically, how do you morphologically transform extended star-forming galaxies into compact star-forming galaxies? Or as Avishai talked about, wet compaction, many different physical mechanisms, but this idea that you're evolving from here to here, and both of these processes are fast, so you call this fast track, going from here to here and then up into the compact quiescent population. To me, from the stuff I've heard at this conference, it raises actually quite a lot of questions. So I'm going to take my time to ask my questions here. First of all, what processes quench the compact star forming? If compact star forming galaxies quench and turn into compact quench galaxies, what processes do the quenching? Is it AGN? I seem to remember a talk at some point, maybe not at this conference, but Guillermo said that a high fraction of objects that sit right here have X-ray detections in candles, which suggests AGN feedback. I've heard other people talk about star formation as a way of quenching. This is a big one for me. I've talked to Avishai and Joel at different times about it. What are the observational signatures? I show this plot at other conferences or do a colloquium, and people can buy that this is going here, but they're like, what's the observational signature that anything from here went over that way? Or another way to put it is, how could we detect an object that is in the middle of this wet compaction or morphological transformation? How can we actually possibly hope to separate all the different possible mechanisms that have been put out there, such as gas-rich major merging, which make compact star-forming objects, or gas-rich minor merging, or multiple cold flows, or violent disk instability. All these ideas, do they have different observational signatures that would allow us to actually try to figure out who's more important at what time for building up this population right here? Another question I have, the idea in the literature is that this evolution from compact quiescent to extended quiescent that we see, this slow puffing up, the main idea is lots and lots of dry minor mergers. And a lot of people put that forward. And so my question is, are there enough observed? Can we constrain the number or the rate of dry minor merging to actually explain all of the buildup of the extended quiescent population today, which is where all big, dead, massive early type galaxies live, in the extended part of parameter space? Thank you. Another question is, are there enough of these compact star-forming galaxies at each redshift to explain all of the growth at late times here? So through a fast track of wet compaction, rapid quenching, and eventually slow movement over there. Does all that hold together, starting with these as the main source, to feed the extended population up there? Guillermo touched on this a little bit, and I'll show an example of that, of trying to explain the buildup of the compact quiescent from the compact star forming, but I'm talking about also going over into the extended quiescent population. And finally, I notice at each redshift there are some, if I believe my morphological classifications, there are some star-forming ellipticals in the extended side of the population. There's not a lot of them, but there's some here, 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 and here. Do they play a role? Could they possibly be maybe perhaps a different quenching or maybe a slowdown, moving from the star-forming population slowly on a different time scale than on this side to help build up the extended quiescent population? Okay, I'm going to try to answer one or two of these questions. This one, so I zoom out here and I go back to number density evolution again. And this time I'm going to look at 3 key spheroidal populations and their number density evolution from this plane. First of all, in blue dashed line are all of our compact star-forming galaxies and their evolution. In red dashed line is the compact quiescent galaxies, and finally in red dotted line is the extended quiescent galaxies. And so we can see there are three different growth tracks over cosmic time. And when I play a little toy model, borrowing a page from Guillermo's playbook, I'm going to just simply fit to the 2 quiescent populations some sort of functional form, and I'm going to try to build up each population. So basically I'm going to take the compact quiescent galaxies and build them up by adding some compact star-forming galaxies that die off in some t fast time scale. But the wrinkle here is I actually am also going to remove some of the compact quiescent galaxies as a sink to feed the extended quiescent population. And that means I also need to have a track for the extended population, which is just the previous extended population plus that sink term. Plugging the sink term in here, I can solve for the compact star-forming number density and do it for a couple different time scales. So I try a very fast 0.3 gigayears and a slower 1 gigayear, and you can see the tracks. And so what I see is qualitatively over this redshift range, 0.3, a fast time scale kind of fits all the data points, but not quite. At higher redshift, it overpredicts. At lower redshift, higher redshift it underpredicts, and at lower redshift it overpredicts. The way I look at it is if you pick something like about a half a gigayear, the curve will go through here. So during cosmic high noon, the number density of compact star-forming galaxies, if they have about a half a gigayear time scale, would explain the buildup of both the compact quiescent and extended quiescent population during cosmic high noon. But then afterwards, it completely fails. It's not sufficient. And this result, this fitting, is pretty robust to different choices in how you select extended versus compact. So here again, you need a longer time scale to go right through those points, maybe 4.4, 0.5 gigayears, but then you're really short at later times. All right, my last slide is the implications of this result. That rapid formation of compact star-forming galaxies and then quickly killing them off can account for both of the quiescent population's growth, the compact and the extended growth, up to about redshift 1, but then insufficient to me, that means there's got to be some other way of building up extended quiescent galaxies, especially at redshifts less than 1, that start to matter more and more. And I feel like there's a hint in here. When I look at the last 2 redshift bins, I see a lot of the quiescent galaxies are actually in the what you might call the transition zone or green valley. And I can imagine that galaxies are sliding this way with size growth, and some galaxies are going this way, and they're coming together to build up the extended population at late times. So this goes back to a question I asked before. I've heard ideas today by David Elbez about the slow downfall. Guillermo in his paper talked about secular processes. Basically, the work to do is to try the same game, but now add another sync term for things coming from the Green Valley and expand with larger samples. I'll stop there.
So the idea that the red arrow up there, that might be able to do with minor mergers. So this is easily testable by plotting on the x-axis not sigma 50, but sigma in a fixed radius. Because the idea would be that minor mergers only add mass to the outskirts.
Right.
So have people done that? Have you done that? Have people done that? And does it indeed show that then there's not much movement?
So Guillermo has plotted at a fixed 1 kiloparsec on the core, but I'm not sure how that would actually translate with how you would see the puffing up, because you're only looking at the core.
Well, that's the idea. You wouldn't see puffing up there. So is that what you see here?
Yeah, Guillermo?
Yeah. Go ahead. We have time to show the evolution of the number density yesterday, but we did exactly that. Since you can have both densities when you look at the fixed central 1 kpc, you can assume that if the cores do not change at all, then you can track essentially the mass growth of quiescent galaxies in the envelope. And the answer is it doesn't match.
It does not match?
It does not match.
Isn't that inconsistent with what Peter von Dokkum has been selling? That he claimed that you really see this growth only in the outskirts?
Well, there are 2 different things. One is if you really see that the central density of quiescent galaxies today agrees with the density of the redshift. That is true. Essentially, it's true. The other question is if you can reproduce the evolution in the sizes of all quiescent galaxies solely growing the ones that you have hydrated. You cannot, and that Marcella will talk about that, is because you are adding new galaxies that are larger. So you cannot explain the whole size evolution by growing hydrated nuggets. You have new quiescent galaxies that are larger. So you have a combination of the 2. If you try to do it just growing red nuggets, it wouldn't work.
Right, which seems like...
I think it is true that you get a cleaner diagram if you use sigma 1 as opposed to sigma 50. And it's interesting to compare them because sigma 50 is sensitive to the outer parts and sigma 1 is not. And the degree of the extension that you're pointing out to the left there is reduced when you use a sigma 1 diagram.
So you're saying this part right here is reduced, right? You won't see this sliding over here.
That's right.
And we've talked about that. I found that, I get that point, and I get that it's more fundamental what's going on in the core, especially when you're building the nuggets. But I wondered if I would not have seen then this hint of something coming through this transition zone at later times.
Well, I think there is some evidence for a completely different track at late times in which one would go more or less directly from the lower left to the upper right.
So like this?
Yes, exactly, bypassing the nugget phase. This is my prejudice, that nuggets today are bursting nuggets in the blue phase.
So in the inner kiloparsec? Because in this plane there are no compact objects at low redshift. So massive, there's nothing that sits here at redshift 0.
Yeah, so what I mentioned yesterday is that
Right?
these 2 tracks into one sequence is that it's the density of the forward mass. So hydrated, you have a naked spot that is dense enough to make a quiescent galaxy.
Yeah.
So you have a disk with a dense spot.
You have to normalize your parameters because sigma 1 is a function of mass. So you need to think about a delta sigma 1, which is what Guillermo was doing in his talk.
All right, you guys are, you're convincing me.
Okay, let's go.
Thank you.
Thank you, Dan.
Zero that Eric Bell and I did a long time ago, and if you integrate, you see that the quiescent population has accumulated most of the stellar wealth by the present time, and this has been going on over all of cosmic history, at least since the last 7 to 11 billion years, and I think of it as something I like to call galactic capitalism, or severe galactic capitalism, in which the quiescent galaxies are the population that are growing, even though they're not doing any of the actual work producing stars. And a little more than 10 years ago, Eric and I used... Well, it seems like it's not echoing to you all?
No.
Okay, it is to me. So from cosmic high noon, think of this as the time of peak galaxy activity. The growth of the quiescent population has been going through, even extending to before cosmic high noon. And that's coupled with the decline in star production. And to me, I always find these two plots together very fascinating. First of all, you see at the beginning of cosmic high noon, around redshift of 3, the quiescent population only had 2% of its stellar wealth. And it had 4 times less number of stars than the star-forming population. And during cosmic high noon, where we had pretty much a very high constant rate of star formation, the star-forming population, the workers doing all the work, they were gaining in mass, but the quiescent population is still gaining much faster. And then with the decline of star formation over the last half of cosmic history, this flattens out and the quiescent population really takes off. So with candles, we can now really explore the role of spheroidal galaxies, and some of our co-authors already have, during the period of cosmic high noon. I'm going to do it slightly different. I'm going to make use of a very significant team effort to visually cleanse with a bunch of members from the candles team, many who are here, and primarily with one of my undergrad or former undergrad students, Zach Reiser, who graduated this fall. A little loud. I'm a little loud. How about that? And divides his time between finishing up this paper with me and touring in a funky jazz band, which is pretty challenging, but he's a good student. So when I think of galaxy evolution, I like to think of the haves and the have-nots. And of this idea, so here we have mass functions from redshift Zeus. The Hubble Space Telescope as part of the GEM survey and showed that this growth was dominated by spheroid-dominated or spheroidal galaxies, early type galaxies, all the same, all synonyms of each other. During the last half of cosmic history, which we could probe from redshift less than 1 to 0 with GEMS and Sloan. Now, this galactic capitalism now has been going on, it seems, from the beginning of cosmic high noon. We think of cosmic high noon. This is a term that either Sandy or Joel coined. Is that true? Pardon?
I thought it was Harry Ferguson.
Oh, Harry. Okay, I should give Harry credit.